All right, so today we are doing IGCSE chemistry, May June 2024, paper 61. So we're doing paper 6, variant 1 of 2024. Let's look at the first question. A student carries out a titration to find out the concentration of a sample of dilute hydrochloric acid. The student adds 25 centimeter cube of aqueous potassium hydroxide to the apparatus labeled A in figure 1.1. All right, so this is the apparatus B, this is the apparatus A, adds of whatever. Let's look at the first question I'm interested in. Name the items of the apparatus labeled A and B. So A is what we call a conical flask, right? A is our conical flask and B is our pipette. Next question. The student adds the indicator after the volume of 25 centimeter cube of aqueous potassium hydroxide has been measured. All right, so he adds the indicator after 25 centimeter cube potassium hydroxide was added. Explain why the student adds an indicator to aqueous potassium hydroxide. Why do we add an indicator? So we can visualize or we can visibly observe the endpoint, right? So we can, so not we can, because the question is about the student, so that he can observe the endpoint of titration. All right, name a suitable indicator. Because he's added sodium hydroxide, a very suitable indicator would be whenever you add in the conical flask an alkali, you add phenolphthalein. Nowadays, phenolphthalein has been changed by its brother thymolphthalein. So we'll say thymolphthalein, thymolphthalein. If someone says, sir, could we write methyl orange? Yeah, methyl orange will also work. But usual rule of thumb is when the in the conical flask there's an alkali, we usually add the thymolphthalein or phenolphthalein. All right. Next, describe how the students can determine the volume of dilute
Sir,
hydrochloric
you
acid.
spelled thymolphthalein wrong. It's PTHA.
THA, thamol.
नहीं वो तो Y से था. The second TH. E is going to be THA.
Oh, the second THA or TH.
Yeah.
THALEIN, thymolphthalein. ठीक है.
Yes.
Describe how the student can determine the volume of dilute hydrochloric acid used in this titration. So how would he measure how much hydrochloric acid was added? Now in this question you can see that this is the pipette, this is the conical flask. Of course, this is how this is a titration. So acid is going to be titrated from the burette. How do you measure the volume used inside a burette? You basically find the initial volume that was, and you find the final volume, you measure the final volume, and then you subtract the two. Okay, so we will say record initial volume and final volume.
Sir, this is added using the burette, right?
Yes, of acid in burette. Stop. Subtract the final volume and initial volume to obtain the volume, to obtain the volume. Next question. The student observes the color change that occur as they add dilute hydrochloric acid from the burette. State one other thing the student should do as they add the dilute hydrochloric acid to the aqueous potassium hydroxide. What should he be doing as he's adding drop by drop the acid? We say we should keep mixing inside the conical flask. So there can't be a glass rod that could be intervening the mouth of the conical flask. So how do we keep mixing? We basically hold it in our hand and we swirl it gently. We call it swirling. All right. So the student should swirl Student, should SWIRL swirl the mixture, yeah, the contents of conical flask?
Can we say stir? Stir the contents or stir the
The
mix,
thing
stir
is,
the.
you
We're not
can't
using a
say,
rod, right?
yeah,
So
you can't say stir because stirring requires a stirring rod, right? स्टीयरिंग रॉड इज नॉट यूज्ड, क्यों? क्योंकि देखें कॉनिकल फ्लास्क की एक ही ओपनिंग है, राइट? देयर इज ओनली वन ओपनिंग इन द कॉनिकल फ्लास्क. इफ यू वर mixing it with a rod, then the burette that would be above it, its drops might fall on the rod and then they could accumulate and all of them going at the same time cause differences in the volumes, right? You want the top to be open so that the drop directly falls into the alkali and quickly neutralizes some of the alkali. ठीक है? So that is why it is better to use the word swirl. So the student should swirl the contents of conical flask gently until the color change occurs. Until a permanent color change occurs, because the color would be changing but then going away as you're swirling, but then there would be a drop that would just permanently change the color, right? Gently until a permanent color change occurs. Full stop. All right. On to the next question now. A student investigates the temperature change when magnesium reacts with dilute sulfuric acid. The student does 5 experiments. Oh my god. Okay, that's a lot of reading. So we ignore a lot of reading. We have a lot of time in paper 6 to read though, but let's just understand what things have been asked so we can see what we can do about it. So this is experiment 1, experiment 2, 3, 4 and 5. All right. So volume of dilute sulfuric acid. So of course we do not know the volume of dilute sulfuric acid. So let's just have to go use 25 centimeter cube measuring cylinder to pour 20 centimeter cube of dilute sulfuric acid. Okay. So in the first one, we had 20 centimeter cube of dilute sulfuric acid. All right. And then in the second one, use 25 centimeter cube measuring cylinder to pour 20 centimeter cube of dilute sulfuric. Okay, 20 for this one as well. And I see for experiment 2, 3 and 4 they've said repeat, 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 right? Repeat experiment 2, adding 4 centimeter distilled water instead of 2, adding 6 of distilled water, adding 10 of distilled water. Okay, so meaning sulfuric acid that was added was 20 for all of them. ठीक है? So that has been cleared out. Volume of distilled water added in centimeter cube. So for the first one, we use a thermometer to measure the initial temperature of acid in the boiling tube, record the initial temperature, add a coiled 5 centimeter length of magnesium ribbon to the acid in the boiling tube. At the same time, start a timer, continue to stir the content of the boiling tube using thermometer. After 45 seconds, measure the temperature of the mixture of the boiling tube, record this temperature, rinse the boiling tube with distilled water. Okay. In experiment 2, it was 25 centimeter cube measuring cylinder. To pour 20 centimeter cube of dilute sulfuric acid in the boiling tube, use a 10 centimeter cube measuring cylinder to add 2 centimeter cube of. Okay, so this bullet point is actually missing, meaning there was no distilled water added in experiment 1. So volume of distilled water added should be 0 over here and 2 over here, right? And then for experiment 3, we had 4 centimeter cube distilled water and 4, 6, and 4, 6, and then the last one is 10 centimeter cube of distilled water. All right. Next, it says temperature after 45 seconds. Temperature at 45 seconds. Oh, thermometer diagram after 45 seconds. So the temperature over here looks like it is 37. All right. 37. This one is exactly 31, 32, 33, 34. This one is 34. Okay. This one is, it is in the middle. If it is in the middle, then it is 31.5. And because I had to write 31.5, this will have to be zero point 0 and this will have to be zero point 0. Okay. All right. On to the next one. 30. All right. बेटा माइक को म्यूट करना पड़ेगा किसी एक को, आपके किसी के बैकग्राउंड में बहुत शोर आ रहा है. Thank you. All right, this will be 30.0 now. And then this would be 25, 26, 27, and 28, and in the middle. So this would be 27.5. So this would be 27.5. All right. And then next stuff, we have temperature increase. So how much temperature has increased from 25 to 37? So just subtract 37 minus 25 is 12. All right, this is 12. Now the next one, 34 and 25.5. 25.5 and 34. We subtract them together. We get 8.5. 31.5 minus 25.5 equals to 6. So I'm basically subtracting these two values. All right. These are the values I'm subtracting. And then this one is 4.0. This we will call 6.0 then, because everything is one decimal place. We have to keep it uniform. That is how it works. This is not supposed to be 12, then this is supposed to be 12.0, one decimal place. All right. 26 and 27.5. I mean, it's 1.5, but you can never be too sure, right? So 1.5 is the temperature change. State which experiment 1, 2, 3, 4, or 5 had the smallest temperature change. So which experiment had the smallest temperature change? Of course, the one with 1.5, that is experiment 5. All right. And then the next question, explain why temperature change was the smallest in experiment you have given in B part 1. Why was the temperature change smallest? Why did the temperature not increase a lot? Why? Because of the volume of water that was added. So there was a very large volume of water that was added, which requires a lot of energy to heat, right? We've discussed in physics as well, you guys have discussed that water requires a lot of heat to heat up, right? A lot of energy is required to heat water up. Water has a very high specific heat capacity. So that is why whenever you keep adding water, the overall heat loss is not going to increase the temperature much because of the mass of water that is used, right? So we will say in experiment 5, why has this? In experiment 5, a very large volume of water has been used. A very large volume of water has been used. All right. So it's only a 1 mark question, so we can just write that much. Next, complete a suitable scale on the y-axis and plot your results from figure experiment 1 to 5. So this is volume of distilled water added, and that is temperature increase. The maximum temperature that we saw increasing was 12.0, right? So let's just count. So this is 1, 2, 3, 4, 5, 6, right? So this top can be 12.0. Why not? And then this can be 10.0, and then this can be 8.0, this can be 6.0, this can be 4.0, this one would be 2.0, so this one would be 1.0, and this is, well, we don't have to draw right 1.0 because it's in the middle, right? So just leave it like this. Okay, now we have to plot the experiment, right? So in experiment 1, volume of distilled water was 0, temperature increase was 12, right? So volume of distilled water added 0, temperature is 12. So on the absolute over here is this one, okay? Next, in experiment 2, volume of distilled water added was 2, temperature rise was 8.5. So 2 and 8.5. So at 2, we should have 8.5 right here in the middle of 8 and 9. So this is 9.0, right? So right in the middle should be 8.5, right? So this is the value of 8.5. All right. And then for 4, it is 6 degrees temperature change, right? For 4.0, it is 6 degrees temperature change. For adding volume 6, temperature change is 4. And for 10 centimeter cube, temperature change is 1.5. For 10 centimeter cube, temperature changes, this is 1.0. So this must be 1.5. So at 10, the temperature change is 1.5 like this. All right. So once you draw all these, okay. So we had to draw a line of best fit, right? So this looks like it's a line of best fit to my understanding and knowledge, right? So this looks like a best fit line. They're probably going to ask us, use your figure, use your graph in 2.1 to reduce the temperature increase when experiment 2 is repeated with 7.5 centimeter cube of distilled water. 7.5 centimeter cube of distilled water. So this is 7.0. This would be 7.5, right? So we want to find out what the temperature change should be according to our line of best fit, right? According to our line of best fit. According to our line of best fit, the temperature increase or the temperature change should be of 2.0 degrees Celsius. All right. According to our line, it should be 2.0, or we could even be more accurate, try to be more accurate. We know that this is 0.5, right? This is 2.5. So meaning each box is approximately 0.2. Each box is approximately 0.2. So this is roughly half box. We could even call it 2.1, right? So we could call it 2.0 or 2.1. That would be the increase in temperature according to us. All right. On to the next question. The average rate of temperature increase in each experiment is calculated using the equation shown. Average rate of temperature increase divided by 45. Calculate the average rate of temperature increase in experiment 1. In experiment 1, temperature increased by 12.0. Total is 45. What is 12 divided by 45? 12 divided by 45 should be 0.267. 0.267, right? Because 26666, so 267. All right, so it is 0.267, and this is degrees Celsius on the top temperature, and this is second, right? So we call it degrees Celsius plus per second. Degrees Celsius per second. How do I know the unit, beta? How do you find out the unit? I'll show the calculation of unit side over here. Basically, you're putting temperature, whether it is delta T, change in temperature, but it is still temperature, and at the bottom it is time, right? So it's degrees Celsius upon second. So unit क्या होगा? Degrees Celsius per second. Next, explain why the results of the experiment are more accurate if the boiling tube is wrapped in cotton wool. If you wrap it in cotton wool, we know cotton wool is a good insulator.
Sir,
Cotton wool, G, is
can
a
you show your graph again for a second, please?
good insulator. Yes, beta.
ठीक है, okay, thank you.
Sure. Okay, cotton wool is a good insulator. So what do we do if we have a good insulator? So it reduces heat loss to the surrounding. Hence, temperature change at end is more accurate. All right. So the temperature change at the end that we have is more accurate. Explain why a 25 centimeter cube volumetric pipette cannot be used to accurately measure the volume of distilled water added. So why can't we use 25 centimeter cube of volumetric pipette to accurately measure the volume of distilled water added, because volume of distilled water added is 2, 4, 6, 10. It is not 25, right? 25 centimeter cube volumetric pipette can only accurately add 25 centimeter cube of water. All right, that is what you have to say, right? 25 centimeter cube, not this, 25.0 centimeter cube volumetric pipette is only useful to add fixed 25.0 centimeter cube of liquid or solution. Full stop. Next, state one other way in which the apparatus can be changed to give more accurate result. Which apparatus can be changed to give more accurate result? Let's see what they have done, which we can correct. Um, Use a 25 centimeter cube and look at that right here, measuring cylinder. Usually when they use the word measuring cylinder, you should know that a question is coming, how can they improve the apparatus to have better, right? So instead, how could you add 20 centimeter cube, uh, how could you add 20 centimeter cube of sulfuric acid to the boiling tube? You could use a burette instead, right? Or a 20 centimeter cube pipette instead, all right? Instead of using measuring cylinder to add H2SO4, use a burette or 20 centimeter cube PIPE pipette instead. Full stop. Next, sketch on figure 2.1 the graph you would expect if all experiments were repeated using a 2 centimeter length of magnesium ribbon instead of 5 centimeter length. So if we used 2 centimeter length of magnesium ribbon instead of 5 centimeter cube, 5 centimeter length, what would you observe? Of course, the heat released would not be as much. So in the first reaction, we would not be going up to 12. We would be going up to 2/5 of 12, right? Because if 5 centimeter long ribbon increase the temperature to 12 degrees Celsius, right? Then our 2 centimeter length would increase the temperature to x. So x would be 12 times 2 upon 5. So 12 times 2 is 24 upon 5 is 4.8. So the in temperature rise should probably be starting from a very lower level, right? So we can duplicate it and we can say the temperature might be like this.
So we just have to estimate.
Yeah, exactly. 4.8 would be like over here. So it probably would be starting like this. And because temperatures though, the gradient would be different. The gradient would not be same because higher temperature shows a greater rate loss of some sort. Like, okay, so that is how you do that question. And then we go on to question number 3. A student tests two substances, solution E and F. Test on solution E. Solution E is aqueous chromium bromide. Chromium bromide means it has Cr plus 3 ions and it has Br minus 1 ion. So get ready to see silver nitrate and acidified nitric acid trying to make precipitates. Let's see. First, record the expected observations. The first portion of solution E, the student adds aqueous sodium hydroxide dropwise and then in excess. Observe the observations of adding dropwise. Beta Cr3 plus has green color, so green precipitates would form. The observation for dropwise would be green precipitates form. All right. And then if you don't remember what happens to those precipitates, do they dissolve or do they remain insoluble? Just go down and keep going down. Here, यहाँ पे आ गया आपका chromium. All right. In aqueous sodium hydroxide, green precipitate is dissolved in excess. In aqueous ammonia, green precipitate which do not dissolve in excess. So in the above one, we see we have added sodium hydroxide. So precipitates dissolve, and you could go ahead and be more fancy about it. Precipitates dissolve giving a green colored solution. Green colored solution. Full stop. On to the next question. To the second portion of solution E, the student adds about 1 centimeter cube of dilute nitric acid and a few drops of aqueous silver nitrate. All right, so he's added silver nitrate and so on. Observation would be creamy precipitate, right? Because bromide ions, they produce creamy precipitate. Next question. All right, बहुत कुछ लिखा हुआ है. Let's look. The observations in test 1 show solid F is hydrated. Okay. Nice. Describe a chemical test to show that the condensation on top of boiling tube contains water. What would be the test and the result? Now the thing is, the test for water is not mentioned over here. You have to remember the test for water, and there are two ways to test for water. One test is that you could use anhydrous copper 2 sulfate crystals, or you could use anhydrous cobalt 2 chloride crystals. Whichever one you use are fine. All right, so I always like copper 2 sulfate because we remember that it is blue in color once it gets hydrated. So we say, okay, add few drops of that liquid on anhydrous CuSO4 crystals. But there was not enough space, so we just said CuSO4 crystals. What would be the result? Crystals will become blue in color. All right. Next question. From the tests and observations in table 3.1, it is not possible to identify the cation in solid F. It is not possible to identify cation in solid F. All right. Why? Give another test that can be carried out to help identify cation in solid F. So what tests have happened and what have not? Heat about half of solid F in a boiling tube until there is no further change. White solid forms a colorless liquid. Steam comes out from the boiling tube and condensation is seen at top of the boiling tube. After a while, the colorless liquid becomes a white solid. What? Okay. The remaining solid F is dissolved in water to form solution F. Solution F is divided into three portions. The first portion, solution F in a boiling, add aqueous sodium hydroxide. That has happened. So we've tried to test with aqueous sodium hydroxide. Well, that did not work. Okay, so warm the product and hold temperature. It must prepare. Well, we failed at that. To the second portion, solution F, add 1 centimeter cube dilute nitric acid followed by aqueous barium nitrate. That was to test for the anion, not the cation. To the third, add few drops of acidified aqueous potassium magnate. Well, aqueous potassium magnate could be added for multiple things, but not to test for cations. So he has not done the flame test, right? So he could conduct a flame test, right? The student, we could conduct flame test. Flame test of solid F. Identify the anion in F. Okay. So because they added 1 centimeter cube of dilute nitric acid followed by a few drops of aqueous barium nitrate and a white precipitate formed, this shows that the presence of sulfate is guaranteed, right? It should contain the sulfate ion, right? SO4 minus 2, right? On to the next question. I think this will be the final question. A mixture contains three compounds: liquid ethanol, solid sodium chloride, solid zinc carbonate. Table 4.1 gives information about these three compounds: ethanol, solubility in water soluble; sodium chloride, soluble; zinc carbonate, insoluble; solubility in ethanol. Well, ethanol is ethanol. This is insoluble. This is insoluble. All right. Describe how to obtain a pure sample of each of three compounds: ethanol, sodium chloride, and zinc carbonate from the mixture. You are provided with common laboratory apparatus. This is a 6-mark question. We will separate each of them. Look, the reason why they have told us that about their solubility is because we will require water, and this is very easy. Look, these two guys, out of them, zinc carbonate does not dissolve, so you start to put all three of them in water, and zinc carbonate will not dissolve, remain as a precipitate. This guy would dissolve, this guy would dissolve. All right. And then what you will do is you will filter zinc carbonate out. Once you filter zinc carbonate out, you will collect it, dry it between few sheets of filter paper, and you will collect zinc carbonate, all right, pure sample. And then you have ethanol in water and you have sodium chloride in water. Now your common sense should tell you what would be able to be collected first. Would you be able to collect sodium chloride first or ethanol first? In your thought process, you should think how to collect sodium chloride. If sodium chloride is dissolved in water, you evaporate the water, and sodium chloride is left behind. How do you collect ethanol from a solution of water? The solution of ethanol and water is the one that is mentioned in the notes as well in the separation and purification topic in the part called fractional distillation, where the example is given of ethanol and water. Ethanol has a lower boiling point, 78 degrees. So you can't evaporate water without evaporating ethanol. So first, let's just fractionally distillate ethanol into a separate flask and collect it so that we have pure sample of ethanol, and then only sodium chloride would be left in water. Then we can evaporate till dryness. Okay, so we will say it, take the mixture and add it in excess water and stir the mixture using a glass rod. अच्छा मैं तो भूल ही गया कि we have to use apparatus names as well. Using a glass rod until no more precipitate dissolves. Meaning once you see that no further dissolution is taking place, stop mixing. All right, take the mixture and add it in excess water in a beaker बोल देते, लेकिन चलो अब तो लिख दिया, अब रहने तो ठीक है, excess water in a beaker कर देते, ठीक है, या फिर यूं बोल लेते कि take a beaker and add the mixture in it, then add 100 centimeter cube of water or something like that, ठीक है. Anyways, once it is completely dissolved, now filter the solution using a filter paper funnel, using a filter paper and collect the residue. Stop. Dry the residue between few sheets of filter paper to collect pure dry crystals of zinc carbonate. All right, so you will have collected pure dry crystals of zinc carbonate. All right, once you've collected pure dry crystals of zinc carbonate, what next should you do? What next should you do? All right, now since after filtration you would have in a separate beaker through the funnel the liquid and the solutes that are dissolved in it, which are NaCl and ethanol, which is C2H5OH, right? This is what we call the filtrate, right? So we will say now take the filtrate, all right, add it, pour it in a round bottom flask and place it in a fractional distillation assembly, right? Add it in a fractional distillation assembly. Once you add it in the fractional distillation assembly, what would happen next? What would happen next? Okay. Once you add it in the fractional distillation assembly, then the next thing will happen is the ethanol will evaporate, pass through the fractionating column, and collect in a separate flask. All right. So place a clean, dry conical flask at the end of the condenser to collect pure sample of ethanol. To collect pure sample of ethanol, right? You want to collect pure sample of ethanol over it. Okay. How do you know fractional distillation is completed? Stop the distillation process once the reading in thermometer placed adjacent to the condenser starts to rise above 78 degrees Celsius. Full stop. All right. So you've collected pure sample of ethanol. You've collected pure sample of zinc carbonate. Now only uh, in the round bottom flask that was in the distillation assembly, only your sodium chloride and water is left, right? So now the flask only contains solution of AQUEOUS aqueous sodium chloride. Full stop. Place it on a burner. या फिर ये सब नहीं लिखो बस just write down that um, heat this solution till dryness to obtain pure dry crystals of sodium chloride. Full stop. ठीक है. अच्छा जी. Did they mention that we have to say? Did they mention what we have to say about sodium chloride? Like, no, not about sodium chloride. They mentioned that we have to talk about any safety features of the reaction. No, they have not. So because they have not mentioned, we can leave these lines empty. If they mention any security, वगैरह, safety, वगैरह. So you will just say कि to heat the round bottom flask, use a use a hot water bath. ठीक है. और दूसरी चीज कि when heating sodium chloride, uh, your glass should be made of pyrex. ठीक है. pyrex glass यूज करें या फिर स्टडी टेस्ट ट्यूब या क्रूसिबल यूज करें या कोई इस तरह का कंटेनर यूज करें, बॉइलिंग ट्यूब यूज करें, which can bear the high temperatures, right? There is also one more thing in the distillation assembly. Most of the times it is not mentioned in IGCSE, but you can remember a safety precaution for distillation assembly. ठीक है. Over here I will write it down. A safety precaution for distillation assembly. ठीक है. Always add anti bumping granules in the round bottom flask. You stop. This prevents buildup of large gas bubbles in round bottom flask during heating, and हीटिंग के दौरान जो है लार्ज बबल्स नहीं बनने देता. एंड व्हाट एल्स डज इट डू? ऑलवेज ऐड एंटी बबलिंग granules in the round bottom flask. This prevents buildup of large gas bubbles in the round bottom flask during heating, and prevents spillage. All right, now for the IGCSE students, what is this? Beta, in the distillation assembly, if I draw a very makeshift distillation assembly, right, this is not fractional distillation, I'm only drawing a distillation assembly. Fractional distillation assembly is only different because it has a fractionating column. All right, so this is what a distillation assembly technically looks like. This is supposed to be a thermometer. Okay, now this is the way for a condenser. All right, this is what we call the round bottom flask. Our sample is over here. This is what is getting heated. So because of the heat, there could be large gas bubbles that could be produced. So we just add some beads, and they are called anti-bumping granules. These beads are called anti-bumping granules, right? These are your anti-bumping granules. This is a safety precaution for distillation assembly that you can remember. Okay, I hope this makes sense. I hope you guys have no questions now. Let me know if everything is clear.
Yes, sir. It's clear.